Okay, we're all set here. This is another double up lecture. We'll go from 11 until 1. We'll try to take about a 4 or 5 minute break in the middle. The handouts today are homework set 5 there. They're also available electronically. Homework set 4 is due here, and I'll pick it up. You can leave it here. Now I have solutions to homework set 4, so if you've turned it in now, you can pick them up. Otherwise, get them from the bin at 5 p.m. when the deadline for turning in homework set 4 is. What I like about the solutions this time is we go into detail on the St. Petersburg problem, and some of the things can't be done analytically, although the questions I've asked can be done analytically. So some can not be done analytically, and you'll see a very curious thing, that even though the expected value of the St. Petersburg game is infinite, if the cost is as much as 10, remember your payoffs are either 2 or 4 or 8, 16, 32, 64 with the probabilities given by the reciprocal of it. So so if the entry fee is 10, you still only want a small fraction of the St. Petersburg game. And the rest you'll keep in cash in your pocket. So if you're a billionaire going into the St. Petersburg game, you'll still be a billionaire coming out, even if the worst possible result of the game occurs. Of course, you might you won't be happy with that investment, $10 in and you get $2 back. But you haven't invested all your money. And in fact, the growth rate of wealth isn't very high for if the entry fee for the St. Petersburg game is very high. So I consider this a pretty good resolution of the St. Petersburg paradox, which is usually solved by, number one, saying your utility for money is logarithmic. That's ultimately unsatisfying because it's arbitrary. Number two, a lot of people say, oh, well, you can't have any game that pays you more money than there is money in the solar system. So they bound the amount of money. That's unsatisfying. Because you always, in St. Petersburg game, you always get a finite amount of money. It's just that it's unbounded. It might be 2 to the million. So that's unsatisfying. Or Feller's solution, which is to say, oh, you only play the game n times, so you want what happens after n times to be positive with high probability, and then you get a resolution that way. So you either bound the amount of money or the amount of plays, or you invoke an arbitrary utility function. Here we see that a St. Petersburg investment opportunity is just part of a sequence of investment opportunities you'll be getting. And if you want to act in harmony with highest possible growth rate, then any cost for the St. Petersburg game is acceptable. But you act accordingly and buy less and less of the game, keeping the rest in your pocket, in order to make sure your growth rate is optimal. Okay, so you'll see at length in the solutions there. Now I have the solutions here, so if you do turn in this, feel free to pick up a copy. That is, if you're turning in homework set 4 now, then feel free to pick up a copy of the solutions to homework set 4 there. All right, last time, which were 9 and 10, we went through chapter 6 on growth rate exponent. Delta W equals I. The value of side information increasing your growth rate is the mutual information. And entropy of English, which will come back today as something we can implement using arithmetic coding. And then chapter 5 on codes. What's a good code? Singular, uniquely decodable, instantaneous, or self-punctuating. The Kraft inequality, which says the code word length L sub I from an alphabet of size D must satisfy this, otherwise they cannot be the leaves of a tree, and therefore they cannot be the code word length of an instantaneous code. And then we used roof codes, where we just took the ideal code word length, log 1 over p of x, for outcome x, realized it wasn't an integer, and took the first available integer greater than or equal to it, to prove that h, the entropy of a random variable, is less than the expected description length in alphabet D, so this is h sub D, less than h sub D plus 1. So we can come within 1 of the entropy with an instantaneous code, and we can never beat the entropy. And the 1 bothered us, so we looked at sequences x1 through xn of length n from a stochastic process, or IID, if you wish, to show that h less than L sub n, the expected description length per symbol of x, less than h plus 1 over n, and this is h sub n in obvious, and I guess this is 1 over n, h sub n. Any case, for stationary processes, they need not be ergodic, but for stationary processes, the expected description length converges to the entropy rate of the process. So that was nice, because the entropy rate has yet one more meaning. See, this goes to the entropy rate, this goes to the entropy rate, and 1 over n goes to 0. So now for any stochastic process whatsoever that has an entropy rate, simply means that this converges to a limit. And for stationary processes, this always converges to a limit. That the entropy rate is a lower bound on the expected description length per symbol. Absolute, can't beat it for an instantaneous code. And we can approach it arbitrarily closely by looking at sequences x1 through xn of long enough length, so that the 1-bit overhead due to the integer round off that you have to do with log 1 over p becomes negligible. So, very satisfactory so far. And this is known really as Shannon's first theorem. That is that, well, should we call that it or this it? We could go and we could see what it is that he states first formally. And so on. So it says the entropy is an absolute lower bound, but it's approachable in expected description length. We've already shown using the AEP that we can approach the entropy just by looking at the typical sequences and enumerating them. There are 2 to the n, h of them, so it takes nh bits to describe one of them. In a way that's a little less concrete and a little more awkward. It's less concrete in that there might be a probability of error because you might get a non-typical sequence. Or if you don't want the probability of error, then you have to do a brute force description of the non-typical ones by just enumerating them, requiring much longer description length, but the average description length stays dominated by what happens with the typical sequences. So you still achieve the entropy limit. So, but you don't get theorems like h plus 1 as an upper bound. Now, today, we finished chapter 5, and we'll show that L is greater than HD. Oh, we've already shown that. Well, but what we did is we used calculus. So I'm going to use the non-negativity of relative entropy to show it precisely. Calculus, we just showed the first derivative, or if you wish, the gradient is 0. That doesn't mean it. It could be a max, a min, or an inflection. This will cinch it down entirely. And then a very interesting way to map stochastic processes into pure coin flips called arithmetic coding. And it's one that's typically used in practice, and it lends itself to your guessing or having a computer guess what the probability of the next term in outcome of the random variable is going to be. And it, you can then design an encoding and decoding scheme that's based on an estimate of the underlying distribution rather than the true, and the cost is only the dp2 distance between the estimate and the true. So Shakespeare puts a distribution P of X on everything Shakespeare can write. Here they are. Here's this book, and here's this play, and here's this, and there's this. And you put a distribution Q of X on all possible sequences of symbols, A through Z in space. And you do optimal